Right, well, welcome back to our next discussion in Chapter 9, where we're going to move into 9.2 now. We just wrapped up talking about sequences and all the things about sequences, definitions, what we mean by convergence and divergence, limits of sequences, properties that sequences can have. So we talked a lot about sequences, and it's important. It's the framework of everything we're doing here in Chapter 9. And what we're going to do now is we're going to take a sequence and do something. We're going to add up all the terms in a sequence. Now that is a very big undertaking because, as we know from 9.1, sequences are infinite. And so that would create for me an infinite sum of terms. And we are going to then try to answer, if we can, what the sum would be if I were to add up all those terms. Now, it doesn't always have to be finite. It doesn't have to give us something. In a lot of cases, it won't. But in some cases, it might. And so we're going to be given a sequence, a sub n. We define what we call the infinite series. So a series is not a sequence, it's a sum of a sequence, the sum of all the terms. The infinite series, or just called a series, to be the sum of all the terms of a sub n, the sum of all the terms in the sequence. Now we have summation notation that we know from Calculus 1, and so we can write it as the sum from 1 to infinity of a sub n, an infinite sum, a1 plus a2 plus a3 plus dot dot dot. Now in general, how are we going to be able to add something up and get something finite back? And we're going to add up all the terms of the sequence. And right away, we can write something down. The first intuition or the intuitive response to this question is, well, we can definitely say when we're not going to get an answer to this question. If the terms of my sequence don't get smaller and go to 0, there's absolutely no chance for us to get something finite back. Just think about it for a second. You're adding numbers up, right? These are values, real numbers, forever. There are infinitely many numbers to add up. When would you ever get something finite back? If you think about it, the only chance would be if eventually in your calculator you start hitting plus 0, plus 0. You start adding up arbitrarily small numbers. That is my only hope in which to get a finite number as a total, if I were to add up all the terms. And so the first response to this question, we actually get our first test, we'll call it what we call divergence test. We have a notion of what we call divergence. We'll define it formally in a second. And that's if the sequence that you're adding up, if the thing that I'm adding up, the sequence that I'm given, if that limit of my sequence doesn't go to 0, meaning the terms that I'm adding up don't get arbitrarily small, then when I go to add up, there's no chance for me to get something finite. Right? In my calculator, if I eventually start adding up any other number besides 0, it's going to blow up. Right? This number is just going to get larger and larger and larger. My only hope would be that eventually I start adding up arbitrarily small numbers, and so we would like it to go to 0. So specifically, what do we get from this? If the thing that I'm adding up, if the sequence does not go to 0, then the series, then when I go to add up all the terms of the sequence, does not exist. What do we mean by that? The term we're going to use is diverges. We'll formally define this in a second. I just want to bring this up. This is our intuition. If the limit of the thing that I'm at doesn't go to 0, there's no chance for this to work. And so our hope is that, well, we're given sequences that do go to 0, that do become arbitrarily small. Now, unfortunately, while not going to 0 is enough to say it can't give me anything finite back, just because the thing that you're adding up does get arbitrarily small doesn't necessarily mean that you will get something finite back. You could actually still blow up. It doesn't go to 0 fast enough, maybe. And what the rest of this chapter, or a lot of this chapter is going to deal with is, well, how do we determine if we do get small fast enough? If the things that I'm adding up do get small and they get small at a certain rate, then maybe we can answer the question of, yeah, it does give us something finite back. And so let's think about how we're going to add up infinitely many things. If you think of it as a whole, that's a very large undertaking. And a lot of times in calculus, we don't like to think of the whole. We like to think of the infinitesimal, the small. And by understanding the small or the infinitesimal, maybe we can make a conclusion about the whole. Think about how integration and all that works. And so in the same way, adding up infinitely many things just from the get-go is too much of an undertaking for me to do. And so instead of thinking of it that way, I'm going to think of it in terms of what we call partial sums. So the first definition we're going to write down is partial sums. So the nth partial sum, we'll denote it by S sub n, is the sum of the first n terms. The first n terms of the sequence. So what do we mean by that? I mean that S1 would just be A1, the sum of the first term, or just the first term by itself. S2 would be A1 plus A2, the sum of the first two terms. S3 would be A1 plus A2 plus A3, the sum of the first three terms. Sn would be the sum of the first n terms in general. And in fact, the limit as n goes to infinity of S sub n, I can't write S infinity, but if we continue this on, and we look at all of these partial sums and then goes off to infinity, well then that would be exactly all the terms added up, right? That would be the infinite partial sum, the sum of all the terms, or the series itself. So the series can be written as the limit of a sequence of partial sums. And that is exactly how we're going to define convergence and divergence of a series. So given a series, n from 1 to infinity a sub n, so a sequence that we're asked to add up, so given a series, so the sum of a sequence, consider the sequence, not itself, the sequence of partial sums. S sub n. So what do I mean? I mean S1, S2, S3, . So the sequence of partial sums. And the limit of that sequence, which is equal to, well, the series itself. If the limit exists, so now we're just back to limits of sequences, which we defined in 9.1. If the sequence of partial sums, if this limit exists, so again, we'll use the word converges to say some letter S, then we say the series converges and the sum is S. So if we look at the limit of partial sums, so that sequence of not the sequence itself, but the sums, the partial sums, and we look at what happens as those partial sums go up to infinity, which in effect gives me my entire series now. If that limit of this sequence converges, meaning it gives me something finite, right? It converges to, say, S, then we say the series converges. That's the terminology we'll use. If the limit as n goes to infinity of the partial sums diverges, meaning it blows up or doesn't settle down to anything specific, then we say the series diverges. And then, of course, there is no sum, so it just diverges. So how do we define convergence and divergence of a series? We look at the sequence of partial sums. So we think of just adding one term at a time. We think of what all those sums would give me, right? So we now have a sequence of outputs, of numbers, being one term added at a time. And if I add one term at a time, we're going to get a sequence of sums. And let's look at what happens to the sequence of sums. Well, the end of the road would be the series, so all of it added together. And if that sequence of sums converges, then we say the series converges and the sum is whatever it converges to. If those partial sums, if that sequence diverges, then of course the series itself diverges, the sum does not exist. And so how are we going to address series or talk about series and find these sums is we're going to think about sequences. Sequences of partial sums is the way we're going to go about it. Now, of course, we're going to learn a bunch of shortcuts along the way, but before we do that, let's put this into practice a little bit. So let's look at a specific series and a specific sum that we're going to be looking at, and let's write out the partial sums and see if we can figure out the sequence of partial sums, if we can get an answer. And so let's say we are given the following. N equals 1 to infinity, 1 over 2 to the n. So say we are asked to add up all the terms of this sequence, 1 over 2 to the n, from 1 to infinity. Well, if we look at this sequence from the get-go, 1 over 2 to the n, we think what's happening here as n gets larger, we see this is becoming a smaller and smaller fraction, right? 1 over 2, 1 over 4, 1 over 8. And so the terms of the sequence are smaller and are getting close to 0. And so I can't say that it diverges. It might give me something finite in this case. How do I know? Well, let's see if the partial sums approach anything. And so let's start writing out the partial sums. So S1 would just be A1. So what's A1? That would be 1/2. S2 would be A1 plus A2. So that would be 1/2 plus the second term, that's 1/4. 1/2 plus 1/4 is 3/4. So far I have 1/2, I have 3/4, that would be the second partial sum. The third partial sum would be A1 plus A2 plus A3, 1/2 plus 1/4 plus 1/8. If I combine fractions together, you're going to get 7/8 as an answer. S4, let's write out one more. A1 plus A2 plus A3 plus A4. That's 1/2 plus 1/4 plus 1/8 plus 1/16. I write out the terms of the sequence and add them up. And if you're good with adding fractions, what you would realize is the sum of these terms is 15/16. And so we have a sequence of partial sums. 1/2, 3/4, 7/8, 15/16, and in fact, we see a pattern here. If we write out the next partial sum is actually going to be 31 over 32. And there's actually a pattern. Now the goal is, what, if anything, are the partial sums approaching? What's the limit of the partial sums? The limit as n goes to infinity of S sub n in general. Well, the hard thing now to understand, and this is why this method isn't going to work for us in general, is we would need a way to figure out what S sub n is. What is the pattern for this partial sum, right? We're not given the formula for the partial sums, we need to find it. We're only given the formula for the sequence. We can write out sums, but now I would need to figure out some sort of an equation that models the sums that I'm getting. In this case, we can figure out the equation. So if n is 2, we get 3 over 4. If n is 3, we get 7 over 8. If n is 4, we get 15 over 16. We would need to figure out a pattern for S sub n in general. That way we could take the limit of it. And this is what makes this method very hard, very difficult. Now I need to figure out a pattern. Well, if we think about it for a second, we're like, okay, well, wait a minute. If it's 1, we get 2. If it's 2, we get 4. Let's think about the denominator separately. If it's 3, we get 8. If it's 4, we get 16. Well, in fact, the denominator, it's 2 to the n. Right? When n is 1, we got 2. When n is 2, we got 4 in the bottom. When n is 3, we got 8 in the bottom. When it's 4, we got 16 in the bottom. So it's powers of 2. That's the pattern that I see there. And then what about the numerator? Well, the numerator is just 1 less than the denominator every single time. So that's easy mathematically. That would be then the numerator or the denominator minus 1. 2 to the n minus 1 over 2 to the n. You can verify it, but that's the pattern that's happening. Well, you can leave it like this, but because I can split a fraction up over a numerator, I can think of this as 2 to the n over 2 to the n minus 1 over 2 to the n. Why would I do that? Because now that first term reduces to 1, and we have this. So now I have a pattern or a formula for the partial sums, meaning if I want the first partial sum, I would plug it in there. Second partial sum, third partial sum, fourth partial sum, so on. And so now we can ask ourselves, we can go back and figure out what is the limit of the partial sums. What is the limit of the sequence? Well, the first term is a constant, so it's not being affected by anything, so we can just think of it like this. And, you know, in sequences, we can talk about limits of sequences, right? Limit as n goes to infinity, 1 over 2 to the n. In fact, we can model this by a continuous function. We can go the f of x route. F of x is 1 over 2 to the x. And in this case, we have 1 over infinity, right? The bottom's blowing up while the numerator stays fixed. That's not indeterminate, that's determined. That's going to 0, which equals 1. And so it turns out, look at this, the limit of the partial sums gave me something finite. The partial sums, this sequence converges. In fact, it converges to 1. What does that mean? That means this series converges. The limit of the partial sums exists, so the partial sum sequence converges. We would then say this series converges. And not only that, you actually know the sum of this series. The sum of this series is 1. That's what it sums to. Now, in general, this method, while it's great, is very difficult, not because of taking limits of sequences. What makes it difficult is this transition of, hey, writing out some partial sums, and then trying to understand, hey, what is there some sort of pattern here so that I can get some sort of function that models my sums. In this case, I could, so now we can take the limit of it and see what happens. And in this case, it converges, it gives me something finite, and that means now the series converges. We'll use that terminology. And while that's a great way to go about it, it's not always beneficial, right? We might not always know a pattern off the top of my head. And so how are we going to answer this question if we don't know a pattern? And so we're going to introduce some shortcuts and some special types of series or special situations that we might run into in which we can get a general formula for the partial sums and therefore get an answer in general. And then the rest of these sections, a lot of sections, chapter 9, deal with, okay, we can't find a formula for the partial sums. Is there some other way of going about figuring out whether or not that series converges? And that's what a lot of these sections in chapter 9 deal with, different ways to go about it. And so what we're going to do now is we're going to say, okay, well, are there certain types of situations in which we can find these types of formulas? And there are. We're going to look at two special types of series. Two special series. We'll call them special because they're series in which we can find a formula for the partial sums. We'll look at one of them in this video, and in the next video in 9.2, we'll look at the other one, which is actually an example of this. The first one we're going to look at is what we call a telescoping series. A telescoping series is a series that has this property here. It looks something like this. B sub n minus B sub n plus 1. We have a difference of things, and they're somehow related to each other. Why is this special? Why can I find a formula for the partial sums if it looks like this in general? Well, let's see. If I look at the first partial sum, that would be b1 minus b2. Right? When n is 1, the first term would be b1 minus b2. That would be s1. S2 would be the sum of the first two terms. So that's b1 minus b2, that's the first output, plus b2 minus b3. Well, wait a minute. Look at what happens here. The b2's cancel, and I'm left with b1 minus b3. And what's S3? That would be b1 minus b2 plus b2 minus b3 plus b3 minus b4. wait a minute now, just like here the B2's canceled, B2's cancel again, B3's now cancel, and what are you left with? You're just left with B1 minus B4. And we see we have this sort of infinite cancellation that's going to happen, right? We can continue on, and in general, S sub n, what's going to end up happening is you're going to be left with B1, that first term. All the ones in the middle are going to cancel, and all you're going to be left with is Bn plus 1, that last term. This is what makes it telescoping, right? Now it's just a constant minus, well, there is a sequence term here, but we have a general formula for the partial sums. And so then we would just need to take the limit as n goes to infinity of b1 minus bn plus 1. Now note that b1 is just a constant, has nothing to do with n, minus the limit as n goes to infinity of bn plus 1. So in this case, with telescoping series, we have a way to find the partial sums. And once we have a way to find the partial sums, once we have a formula for the partial sums, then we can answer the question of convergence, because then it just amounts to, okay, what are the partial sums approaching? And in this case, then it just depends on the limit of the second term, bn plus 1. If this limit's finite, then we'll have an answer. We'll have b1 minus whatever this number is. If this limit does not exist, then of course we will not have an answer, and then we would say the series diverges. And so telescoping, even though it is an infinite sum in nature, is kind of like a fake infinite sum. Why do I say fake? It's because, well, you're really not adding up infinitely many terms. Everything cancels except for a handful of terms. In this case, 2 every time. And so what would an infinite series of this form look like? We'll be explicit first. 1 over n minus 1 over n plus 1. Maybe something like this. Okay, well, let's write out some partial sums. Let's go about it just like we did in the last example. That would be the first term, so 1 minus 1/2. I'm not going to simplify it because I want to see something that happens. S2 would be 1 minus 1/2 plus 1/2 minus 1/3. That would be the first term plus the second term. S3, 1 minus 1/2 plus 1/2 minus 1/3 plus 1/3 minus 1/4 when n is 3. S4, or one more, so we see it, 1 minus 1/2 plus 1/2 minus 1/3 plus 1/3 minus 1/4 plus 1/4 minus 1/5. And what we see happening every single time is we have this sort of cancellation happening. And in general, we can now say that we have a formula for the partial sums. Sn in general will be then 1 minus, well, 1 over n plus 1. That's the pattern that I see, right? When it's 4, we get 5, 3, we get 4, so on. And so we have a formula for the partial sums. Now that I have a formula for the partial sums, now it's just a matter of asking ourselves, what are these partial sums approaching? That would answer my question. That would be the infinite sum. In this case, we get 1 minus whatever the limit as the second term goes to infinity. Because 1 is just a constant. Well, here we see the second term, the numerator is fixed, the bottom blows up to infinity. That's not indeterminate, that's going to go to 0. And so we're going to get 1 minus 0, which now gives me a finite number 1. And so what do we have? The partial sums converge to 1, and therefore this series converges. And the sum is 1. So the sum of this series is 1. Telescoping, right? There's this special type of series. Looks a certain way. Let's look at another one. Might not always happen that consecutive terms cancel right away, but we still have a notion of infinite cancellation. And so let's look at maybe n equals 1 to infinity. Maybe it's like 1 over n minus 1 over n plus 2. Let's see what's going to happen here. We're still going to get cancellation. Let's write out the partial sums. 1 minus 1/3, 1 minus 1/3, plus 1/2 minus 1/4. Right, because it's n and n plus 2. So it's 1 and 3, 2 and 4, S3, 1 minus 1/3, plus 1/2 minus 1/4, plus 1/3 minus 1/5, is 3, S4, 1 minus 1/3, plus 1/2 minus 1/4, plus 1/3 minus 1/5, plus 1/4 minus 1/7. Okay, so let's see what's happening every single time. In this case, nothing cancels. In the second case, actually nothing cancels either. And then finally, once we write out the third partial sum, we start getting some cancellation. So we have 1/3 cancels again, and now that 1/4 cancels. And if we write out the next term, what's going to end up happening is then the 1/5, minus 1/6. If we write out the next term, remember it's going to be plus 1/5 minus 1/7, and so now the 1/5 will cancel, and then we're going to get the next one 1/6 minus 1/8, so then the 1/6 would cancel. And so actually, if we write out the nth partial sum, the nth partial sum, we actually are going to get two terms that remain. One is never going to cancel, and actually 1/2 is never going to cancel. The 1/5 will eventually cancel with this term here. The 1/6 would cancel with the next term over there. And so on and so forth. In fact, we're going to get infinite cancellation, and all we're going to end up with in general is 1 plus 1/2 minus, okay, well, what terms won't cancel, right? We actually didn't cancel this one. We're going to have the last term 1 over n plus 2, and also minus 1 over n plus 1, the one right before it as well. And so in general, we're going to have a minus 1 over n plus 1 minus 1 over n plus 2. We're going to have the last term, the 1 over n plus 2 term, and also this term, right? We're going to get two terms that don't cancel and two terms that do. Two terms that don't cancel and two terms at the end that eventually will cancel, but look something like this. More importantly, now that we have a formula for the partial sums, when we take the limit, I won't write the whole thing again, but when we take the limit of s of n, we're going to end up with 1 plus 1/2, the two terms that are constant. Both of these terms are going to go to 0. So minus 0, which is 1 plus 1/2, or 3/2. So we still get an answer. And so it might not always happen that they cancel directly right next to each other, but hey, if at some point we have this infinite cancellation, if all that remains is, some finite number of terms at the beginning, and then terms that don't cancel in those partial sums, if they go to 0, or go somewhere, in this case they both go to 0, then we get an answer. So it's still telescoping, it's just not like directly telescoping, it's not canceling right away, you might have to wait a term, right? That's because of the 1 over n and 1 over n plus 2, right? The denominator is now 2 away, so it takes every other term to start canceling. But it's still telescoping. And then, of course, well, what if it's telescoping, but maybe it doesn't look telescoping at the beginning? So let's look at something like this. 1 over n squared plus n. You're like, wait, I thought, we had to be a fraction, yes, and it had to be subtraction, and we had to have this cancellation. I agree, it does. It has to look a certain way. It has to be telescopic. It has to be this infinite cancellation, so I'd like to have a subtraction of things. This doesn't look like a subtraction of things, it's just a fraction. And then I remember something from chapter 8 that actually has nothing to do with integral calculus. It just has to do with taking a fraction and breaking it up into pieces. That's partial fraction decomposition. And since I have a rational function, I can do partial fraction decomposition. It turns out that this polynomial in the bottom factors into n times n plus 1. So we can factor it into something like this using partial fraction decomposition. And okay, well, using my tools of partial fraction decomposition, we're going to clear our fractions. We're going to get 1 equals a times n plus 1 plus b times n. N is free to choose, and so n will choose to be 0, for example. That will allow me to find a, so that tells me that a is actually 1. It's gone, and then 1a equals 1. And the other one would be n is negative 1, that way the a term's gone, and then we get negative b equals 1. So b is negative 1. That's great, because that's actually going to give me subtraction. And so what does that mean? That means that this series can be rewritten using decomposition as this series. Well, wait a minute now, that's telescoping. And now I'll use the fact, write out the partial sums. This is exactly the example we just did right before this, and we'll have an answer. And so sometimes it may be disguised as a rational function, but maybe if you use some other tools, right, partial fraction decomposition from chapter 8, you may be able to decompose it into a difference of things, and then hopefully it becomes telescoping. And so that is one example of a special type of series, what we call telescoping. It's a series in which we can make our way through and figure out a formula for the partial sums, and then hopefully get an answer. In the next video, we're going to look at one more special type of series. That's what we call a geometric series, and that is another type of situation where we're going to be able to find a formula for the partial sums, and therefore get an answer. That one's more interesting because in that case, here we get infinite cancellation. It's like, hey, it is an infinite series, but it's really not because there's only a finite number of terms to actually add up, right? The nth partial sum is just 4 terms. And so it's not an infinite number of terms in general to add up. It's just finite. And those terms go to 0. So we get an answer. We got lucky. In the other example, geometric series, we actually are going to be adding up infinitely many things, and nothing's going to cancel. But we're still going to be able to get an answer. And so in the next video, we'll look at the other special type of series, which is geometric, and that will wrap up 9.2 before we then move on and talk about, well, what if we can't find a formula for the partial sums? How can we still answer this question? All right, so 9.2 will wrap up in the next video with geometric series.